Hey everyone, it's time to do day 3 of Advent of Code. But first, I just want to say meeting up with everyone yesterday was super fun, and we had some really great discussion, including, oops, don't look at my lab Slack page, including Mateo is doing. I hadn't been looking at Mateo's code very closely, but I realized he's been doing all vectorized solutions. Oops, don't want to look at that. All vectorized solutions to these problems, which means his solutions are really quite fast. Which, for things like this, for these early day challenges, the difference between it taking, a couple milliseconds and tens of milliseconds is really not perceptible. But, if you're actually coding stuff for real data analysis, it can be. And it kind of made me want to point something out, which is, oh no, this was in Adams. I had another thought of something to point out, which is that when I was first learning to code, I always kind of felt like I had to just be able to understand what was going on, and that I should be able to just read it and understand it. But something we were doing yesterday that is something or at least I end up doing quite a bit is or maybe it was Mateo's. Anyway, I think if you ever don't know what's going on, just one of the huge advantages of Python is that it has an interpreter, right? You can just type commands in and see what comes out. So yesterday, for instance, there was some part of a line that I was having trouble understanding on my own, and so I just made a list really quick, and then I said, okay, what is test 1 colon, and then test colon -1, and then just seeing what the result is there, you can then go, oh, now I get why they had this in this line, and then that'll help you understand everything else better. And that's not a cheaty way to do stuff. That's just, rather than spending a while googling what does this have, what does this make, blah blah blah, to get someone on Stack Exchange to tell you, it's right there. You can just do it, which is not true in languages like C or stuff that's compiled. So with that all out of the way, I have pulled up day 3. I've set up the environment. I, of course, forgot to download my data again, but I can just edit that out. In fact, let's do that right now. So I'll just download my puzzle input. Hopefully I remember to edit this out. This is going to be really embarrassing. Okay. So now we've got the input data. Today's challenge is interesting. It's the first part. We're trying to find the most common bit in each of these bit positions, and then we want to find the least common bit in each of those positions, and then we want to multiply the decimal representation of those two binary numbers together. And how would I do this? The kind of obvious thing would be to you could go through and count everything. But what else could you do? You could split the number into its kind of component integers and then sum them, and then divide by the number of input numbers we have. And if it was greater than 0.5, that would tell you that the average bit in that position, if it's greater than 0.5, is 1, or the most common rather bit. Presumably there's an odd number of input numbers, or else there's a potential for an unsolvable problem where there is no most common bit. But let's try that. This might be the first example. I was thinking I'm going to try and keep all these videos less than 10 minutes. So if it takes me longer than 10 minutes to write out a solution once I've thought of it, I'm just going to compress that, but let's just try that. So first we need to get our input numbers, which I think I want to keep them as, I think I actually want to make them lists for right now. Well, okay, let's get the numbers first. So I think what I want is diagnostics is list x for .r strip for x in input. And then oh, you know, maybe I think Mateo might like this. I might try and use NumPy for this. I'm going to say NumPy. I know that's not right, but now we get to, this is going to be where I don't just know how to do it all off the top of my head, so we get to watch my terrible process. Let's see. And then let's just print this to see, make sure that I'm getting what I think I'm getting. Okay, great. So now we've got a list of these NumPy arrays, which you can see they've got the integer representation of each number in each position. So now sum array equals sum bit arrays. Great, and then av array equals bit arrays divided by len diagnostics. Is it? Oh God. So now I need to look up the vectorized division. Sum array. Oh, did it give me a list? Oh, it's a list. Oh. Whatever. That's fine. Oh, it is if I do np sum. Is that what I want? Nope. Huh. Well, let's just. Oh, I bet if I do this. This is probably disgusting. I can't wait until Mateo tells me how wrong I did this all, but that's okay. I'm practicing in public here. Okay, so that's still not what I want. Let's just go back to how I had it. And, you know, it's not going to be perfect, but so then av array equals x over len diagnostics for x in sum array. Oh. Okay, so we can see, oh great, it worked. We can see here now that basically what I've got is the average bit position. And then we know that if the average bit position is greater than 0.5, that means the most common bit there is 1. And if the average bit position is less than or if the average bit value of that position is less than 0.5, that means the most common value there is a 0. So now what I just need to do is make a new list that has replaced basically what I'm going to do is I'm going to make a list of strings. Well, I'll probably make a Boolean list, convert those to integers, and then concatenate those into a single integer, and then read it as a decimal. So let's do that. So array equals x greater than 0.5 x in array. You're going to hate this. Okay. Okay. Okay, so now I've got gamma. I did it in kind of a gross way, but I'm trying to kind of keep it quick and understandable for the video. Now, the nice thing is we don't have to do all that over again for the what's the other one called? Epsilon. The epsilon rate is the least common bit for each position. And if there were more than 2 choices, we would have to do that all again. But since it can only be a 0 or a 1, we can use binary XOR with all ones. So XOR says if it returns true, it returns 1, if and only if the one of your 2 inputs is 1. The other one has to be 0. So if you think about what XORing with a 1 does, is if the bit you're changing is a 0 and you're always XORing with a 1, then it's going to be a 1. If the bit you're XORing with is a 1, it's going to be a 0 because they're both 1 now. So because of that, XORing with all 1s basically just flips all the bits. And so after saying that, I forget actually what Python XOR is, so I just have to look that up. I like Stack Overflow. They usually know what they're doing. Let's see. I don't want to do bool. Is there really not a bitwise? Oh. How funny. There we go. Okay, so it's up caret. So, how many bits are in? Okay, so now what we can do is we just need to get the all ones string, which we can kind of do a cheaty thing where if we do int and then 1 times len gamma array, which we have up there. So this is going to create a string of all ones that's the same length as this gamma array we made earlier, which is then the same length as gamma, which I guess we could have used gamma as well. So now this is the all ones string as an integer. So then what we can do is epsilon equals this XORed with gamma. And so if we print epsilon, oops. Let's see if my little plan worked. Oh, we don't have any way to know. I mean, they look right, but there's only one way to find out. Let's print this. Great, so that's the right answer. So again, just to walk through it in case I had to shorten anything. The first thing we did is we read in all the diagnostics as lists. So that way each number is its own separate item in a list, and each diagnostic is its own list. So now we have a list of lists. Then we convert each of those lists to a NumPy array with the data type int. So now we have taken our list of lists, which are all strings, and converted them to a list of NumPy arrays, which are all integers. Then we summed across all those arrays, and that's something that NumPy is really good at, is really quickly going through and summing across all these arrays. Then I took the average array, which is at each position of this sum array, I divide that position by how many input diagnostics we had to get the average value at that bit position. And then, since we know that if the average value for something that can only be either 0 or 1 is above 0.5, we know that the most common bit at that position was a 1. So you can just convert that to a 1, and then if it's not, it'll be a 0. So what I did here is a little hacky, is if x is greater than 0.5, that becomes true, which as an integer is 1, and then I made it a string, because we want to join these into a single number, which you have to do with strings. So then we convert that to an int in base 2, and then epsilon is really easy from there. You just XOR against, you XOR in all ones against gamma to flip all the bits, because we know that the least common bit is the flipped most common bit, and then print the multiplication. So this is part 1. Well, I suppose this is part 1. So now let's see what part 2 is. I think for this one, this certainly may take me more than 10 minutes to write. Okay, so that took me way longer than I expected. I think probably because I was trying to do too many things at once. I was trying to make this video, trying to teach myself NumPy, and trying to kind of do like bit masking sort of in my head. It was not a good idea. So I ended up doing a totally different solution just because I've been working on this for over an hour now, and I'm kind of done with it. I ended up using a regex solution, which I'm sure Matteo will make fun of me for, but that's okay. So what I ended up doing instead of trying to be clever with bit masks and everything is we're basically trying to just go through and see um, does the list of items have a 1 or a 0 in each position. And even though probably the like canonical solution would be to do some kind of bit masking solution and build up a mask position by position, I tried to do that a couple different ways. I tried using because then you can vectorize it, right? You can vectorize the AND operation and blah, blah, blah. And I tried doing a bunch of stuff, and I just couldn't figure it out. So I'm excited to see what everyone comes up with. I ended up doing a string-based solution. So each of these functions is the same, it's just they build the mask opposite. So I'm just going to go through the oxygen scrubber, but the CO2 scrubber works the exact same way. So oh, and I apologize if the video looked weird in the middle there. My computer started to overheat, and that's why I've changed the setup of this camera, because now it's doing less video encoding. And so at a certain point, my text editor was running at 3 frames per second, which is just not enough to get any work done. Probably another reason I couldn't figure out my bitmask solution. But anyway, right now, the first thing each of these functions does is if the length of the input is 1, it just returns the integer form of that. And then it makes something called a 1 mask, which is the current mask plus a 1. And then rather than convert it to integers, I just do a regex match. So you can see down here, I initialize each of these masks with an up caret, which means start at the beginning of the line. So it won't match the pattern if it's in the middle of the line. It'll only match at the beginning of the line. And so for every position that matches, or every bit element of the list, diag stands for diagnostics. If it matches, I count a 1, and if it doesn't match, I don't count at all. Then if the sum of the length of the ones that match a 1 is less than the length of the diagnostics, we say that the mask should have a 0 there instead of a 1. Otherwise, the mask is the 1 mask, and then we return the list, and then we make the list. We filter the list of diagnostics to only those that match our correct mask, and then we return the recursive function. So eventually, we get down to a single element which matches the mask perfectly, or is the only one that matches the mask as we have it. And then CO2 scrubber does the exact same thing, except for if the sum of ones is less than the length of the diagnostics, meaning that the 1 is the less common bit there, then we use the 1 mask instead of up here we use the 0 mask. Whew, okay, so again, I don't actually think that was that hard of a challenge. I think I was just trying to solve it in a way that I'm not really ready to make a video about solving it in that way yet. Certainly, if I didn't have to worry about all that stuff, maybe I could have figured it out. But anyway, that was this week. I am really excited to see what you guys come up with. I'm sure that someone has a clever solution. Anyway, okay, thanks. That's why they say practice in public, make sure everyone can see all your mistakes.